Okay, so my name is Chirag Javad. I'm a research scientist at IBM Almaden Research Center, which is in the South San Jose area in California. And I will be introducing GneissWeb. Don't be alarmed by the very hard spelling of this word, and I'll tell you where the origin of the name is. GneissWeb, a state-of-the-art large language model pre-training data set that IBM Research has just introduced, and we will show you how that was obtained, what models were used, and so we go through the whole history of how did this data set came about and how you can reproduce that data set. The word nice is some sort of, it means it's some sort of an igneous rock that is created from solidification of magma and lava and so on. And the reason for picking this name is IBM's AI models in general. You may have seen this. They are called granite, and so to continue with that tradition of using granite for our open source AI models and so on, we picked the name Gneiss for this. Okay, so let me jump in to what I'm going to be talking about. First of all, at a glance, I'll show you what this whole presentation is about, and then some specifics about GneissWeb itself at a high level, and then overview of the recipe. And by the word recipe, it means a very specific thing in the context of LLM applications and so on. We will get into that, and then I'll show you a summary of the results that were obtained that show the superiority of this data set. And then I will talk about my own role, which is something called Data Prep Kit. It's an open source set of tools, and it's a toolkit for data processing, data cleaning, data annotation, filtering, annotation, and so on, to make it better quality and more appropriate for both pre-training stage of creation of AI models, in addition to post-training applications like fine-tuning, RAG, and so on. So my role is a software architect in the Data Prep Kit part of the organization, and so this talk today is more of an introduction to GneissWeb. And if there's interest in learning more details of GneissWeb, we will have the researchers who actually did the GneissWeb itself and come up with the idea of creating these models to give you a deeper dive on the GneissWeb. So I'll at a high level, I'll talk about GneissWeb, but I don't know all the details, and hopefully at some point a follow-up will clear that up for you. But I'm hoping that I give you enough of a introduction to it so that you get interested and you want to know more. I will show you, because of the Data Prep Kit, I show you a notebook, a recipe notebook. We will go through it together, a Jupyter notebook that will show you exactly how it was used to create on a sample data. And that notebook is open source. It's available to you. I'll show you where to get it, and you can go download and play with it. I'll take you through some of it. I think at some point, Dave, we may create some sort of a tutorial in which we will actually go and run the notebook together with the audience. But today I will just show you the various cells of that notebook. So finally, we summarize everything that we've said up to this point. So let's get to this at a very high level, this so-called executive summary and such things, when we want to say a few words about what this is about. So IBM prides itself in creating responsible AI technology, and of course this means transparency in training data, the way, how, and where, and how was that data created. So So when we did NiceWeb, we wanted to actually show you exactly where it came from, what recipes were used, and so on. So you can go ahead and completely replicate what we did. So openness of exactly how we did this. The announcement is very recent. It is on only on February 21st, less than 2 weeks ago. It was announced, and if you get these charts, I'm going to give you the charts at the end of this talk. They will be available for you, and if you click on any one of the hyperlinks that you see on this, it will take you, for instance, this one will take you to the exact the announcement, which has a lot of details in it. So we will go over how it was created. We discuss the tools and techniques that were used in creating it, and finally we go through the Jupyter Notebook recipe. Okay. So what is it? What is this GneissWeb dataset? So this dataset was built on top of FineWeb, and Hugging Face introduced FineWeb version 1.1.0 last year, and we have since then they have introduced FineWeb version 1.2. That is the last bullet that you see here. But what we did, our experiments were done with 1.1.0, and everything that we did could be replicated and done starting from the latest version of FineWeb. In any case, so FineWeb, it has 15 trillion tokens, and it is taking 44 terabyte of disk space just to have that whole data set. So it is derived from 96 common crawl snapshots and focusing on English text and a series of processing steps, language classification, deduplication, heuristic rule-based quality filters, and so on. And after doing all of this, they showed that they outperform the models which were trained on other publicly available data sets: C4, Refined Web, Dalma, Red Pajama, Slim Pajama, the Pile, all of these. But again, these are all hyperlinks. You will, if you click on any one of these, it will take you to where those data sets came from and the history of those data sets and so on. So so starting from FineWeb, which has been shown to be superior to all of those other ones, we started from that, and then we created GneissWeb from that, and we will show you that the fact that we created a superior data set by sort of measurement or the metrics that are evaluating the performance of various data sets. So, okay. Let's talk a little more on what this is. Again, we the goal was to distill about 10 trillion high quality tokens from the 15 trillion that we started from. And unlike the FineWeb EDU, which is also obtained from FineWeb itself, we rely on a single quality annotator that performs aggressive filtering, and this ensemble of quality annotators, there is a sort of a trade-off here between the quality and quantity of tokens retained. So there's a fine balance as how many of these tokens and how many of these quality filters you apply to hopefully make your data better. So we think that we reach some sort of a balance on quality and quantity of data that was obtained after all these quality filters that we introduce. So let's quickly talk about the recipe that was used on top of FineWeb. So again, starting from FineWeb, we applied these sort of transformers or these modules, and we will get to the detail of each one of them, what exactly each one of them means. What does it mean to do exact substring deduplication, quality filters, category classifiers, readability score. tokenize. This is sort of a summary, a very high-level summary of the recipe that was, and by recipe, again, that's, remember at the beginning I said the meaning, the very specific meaning of recipe is it means which one of these transformers, which one of these modules you use in what order, and that order and the sequence of the things that you apply to your original data, that's your recipe. So this is the recipe. It's applying these 5 various modules and they are all coming from the thing that is near and dear to my heart, the data prep kit, which has a collection of all these transformers for processing data. So we use these particular 5, and these particular 5, they are all also available now on the data prep kit open source repo that we have, and we can talk about that also. So
yeah, and I just shared that in the chat link.
Okay,
the GitHub repo for data prep kit.
Oh, thank you, Dave. I'm glad you are.
Maybe folks, to be polite and go check it out. Maybe if they like what they see, give it a click on that star.
Yeah. That's again, that is my own group, and my own contribution is the data prep kit. So okay, so let's look at very quickly at the summary of the results that were obtained after doing all of that, after taking it through all these filters and annotators and so on. So we to compare GneissWeb against baselines, and baseline being things like FindWeb itself or FindWeb EDU and so on. We trained decoder models with 1.4, 3, and 5 and 7 billion parameters on a Llama architecture, and so yes, and this was all done on a load sharing facility cluster, which each one of the nodes has only 8 H100 GPUs. So this is not done with a large cluster of thousands and thousands of GPU cards and so on. So it's kind of manageable what we did. So we evaluated the ablation models to see the effectiveness of things that we were trying using a language model evaluation harness. Again, this is open source. You can the link here takes you exactly what that harness is about, and 2 categories of tasks. So let's look at the diagram together and see what about. So let's imagine, okay, so the top line here, the yellow sort of pipeline starts from FindWeb, 3 snapshots of FindWeb, 703 billion tokens, and then does some random sampling and picks 35 billion or 100 billion tokens. It trains models based on what we said above, either the 1.4, 3, and 7 billion parameter models. It evaluates models based on some metrics of performance and then benchmarks, and I'll show you in a little bit what those benchmarks are. But you do exactly the same thing at the bottom line, but instead of starting from the FindWeb, you start from the same starting point, but the first step that you do, you take it through the recipe steps. Recipe step meaning those 5 things, those 5 transformers that we showed you, and that allow you to increase the quality of data, and then we go through exactly the same model, same everything, same sampling, and so on, but with this more refined version of data, and then we compare the performance that we get from the top line with the yellow pipeline with the performance that we get from the blue pipeline. So okay, so what do we get? What do we get out of this? So remember that I said that there are three models, 1.4, 3, and 7 billion. Here we are only showing the results for the 1.4 billion parameter model, and if you go to the announcement that I showed you, the link on the announcement, you will see the similar results for the 3 and 7 billion. In all of them, you get this is the kind of performance gain that you get by comparing FindWeb itself with the GneissWeb and with the FindWeb EDU. And in all of these cases, you will see that on the average, you get like about 2% or a little more in some cases advantage by by using GneissWeb. And I think I may have picked this the wrong way, because if you actually do pick, instead of the 1.4, you pick the 4 and 7, I'm sorry, the 3 and 7 billion parameter models, you get a little more advantage. But in general, it's a couple of percentages, and that is still very significant in pre-training to get a couple of percentage by just picking better data for doing this. So how are the scores calculated? The scores are calculated based on these metrics of an average of these common sense reasoning, language understanding, reading comprehension. These are tasks. So based on the average score of all of these tasks that are generally used for evaluation of large language models and so on, this is sort of the gain that you get by using GneissWeb. So, okay, again, more details are will be available if you do a follow-up, and we will bring in the real subject matter expert who picked these particular transformers for data and so on. So our job was based on what they have picked to create these particular transformers on the IBM Data Prep Kit open source. This is the link that I think, Dave, you shared with people. So if you click on this link, it will take you to that page, and we will be I'll also at some point I will take you to that page, because I want to show you where the notebook that has the recipe, we put that notebook that has the recipe for GneissWeb under the same repo. So when we go there, when we get to the notebook and talking about the notebook, we will go, I'll share my browser, and we will go to the repo, and we will get to that notebook, and then we will go through it together. So that Data Prep Kit is a collection of many different transformers and filters and annotators for data based on various criteria and so on. And remember that we said that these 5 particular ones: exact substring deduplication, readability score, extreme token filter, fast text, category classifier, quality classifier, these are the ones. These are the 5 major ones that were used, in addition to something that at the end, of course, filters out what we don't want. Filter itself is another very general transform as part of Data Prep Kit. So let's go through a little bit of detail on each one of these and what exactly means. So let's start from exact substring deduplication. So we apply this to remove the substrings of predetermined length that are repeating more than once, and the sort of the reference for this is, again, it's highlighted here. You will click on this on Lee paper and the suffix arrays and so on. It will tell you some of the details of where we got our inspiration. We did take the inspiration from those, but we did our own customization of this. And again, a little more detail, maybe more than what you would want to know at this point, but it's at the sort of the sub bullet here that we shard each one of the snapshots of FindWeb to roughly equal sizes, and then apply this exact substring deduplication for each shard independently, and then rather than removing all of the duplicate substring, we retain the first occurrence, and so on. So a little more detail that maybe you wanted to know, but just give you a little more detailed flavor of exactly what was done in that particular model, the exact substring deduplication. So remember this page that there are 4 other boxes on this: readability score, extreme token. That's just in the next couple of pages. I don't have the picture in front of me anymore, but remember that there were 4 other things. So let's talk about the other 4. Readability scores. So readability scores are formulas that are based on text statistics, sentence length, average number of words, number of syllables, and so on. And again, there's a reference here that you will be able to click on this designated to assess. It will get you there, and it will show you how these readability scores and categories and so on, this is high quality readable or less quality readable and so on. What are the categories and what are the scores and so on. So we we apply these readability scores and that facilitates for us identifying the ones that have low quality scores, and of course at the end we will filter out hard to read or low quality documents. So it's kind of obvious what this is. Then the fast text quality classifier. Okay, so fast text, for some of you who are familiar, is a family of binary classifiers, and it's been shown that it identifies high quality pre-training documents. This is open. You will click on the fast text. It will take you to the details of the fast text family of classifiers. Specifically, the Datacomp language model trained a fast text classifier that was on a mix of instruction formatted data, and in addition to this DCLM fast text, which we use, we trained a custom fast text classifier using synthetic data. And again, the combination of both the DCLM plus the custom one that we created with synthetic data and so on is very effective, and it identifies again higher quality documents that should be retained and filters out the lower quality documents. Category classifier. Okay, so we found out that the quality score distribution in certain categories that are like science, education, technology, computing, and so on, they have different distribution than the overall things that is mix of everything. So since we know that these kind of documents that are belonging to these categories are sort of higher quality, we annotate which document, and we say this document falls into science, this document falls into education, and so on. And again, based on some filtering criteria, we remove some of the documents, again with lower quality, based on this classification of whether, again, because these categories, they indicate to us higher quality stuff, higher quality documents. A very interesting one is the 5th one, extreme tokenized document. And this is very kind of novel way of doing things. We propose annotations that leverage both the information that we have before tokenization, pre-tokenization stage. So before we tokenize, we have document character length, we have document size, and so on. And then after we do tokenize, we have token counts. So we look at the pre-tokenization information, look at the sort of the document in the middle, the pre-tokenization information, the document character length, document size, and so on, and the post-tokenization token counts. And then we calculate tokens per character or tokens per byte. And if we see very low values on tokens per byte, for instance, we designate these documents that these are extreme tokenized documents, and we should be in a subsequent filtering with the ones that are designated as extreme tokenized, they should be removed. And so again, that's a very sort of novel way that we did. How am I doing with time? Okay. So I wanted to kind of spend some time on the actual notebook, because that's for those of you as the software engineers and so on. This is too much theory here, and then you want to see how it was actually applied in some code. So again, let's do a quick summary here of again all of these things, and the recipe. It says I go the top row on this. I for both, we have two recipes here. Recipe one does exact substring duplication, and recipe two also does that same step, but then you go either the top row, the top part of that diagram on the right, so you do readability, fasttext, category classifier, and so on. Those are in AND. These are logical things. You do A and B, A and B, or you do A and C. So and that would give you the GneissWeb data set as a result of doing this sort of this recipe that you see here. Okay, so we are at the point that I want to take you through the actual notebook that would allow you to go and do exactly what we did. So so let me, if I click on this here, it should take me to the web page. So now I need to, I guess, go back, and instead of sharing the, let me stop presenting here and let me go and share my browser window. Hopefully that will be okay. So do we have, can somebody verify that you are looking at my browser window?
Yep.
Okay. Okay. So this is the actual notebook. Let me do one thing before. So remember that the repo itself that we shared with you. So this is the data prep kit repo, and in the data prep kit repo we have examples. We have these individual transformers that were used. So for instance, for language, for code, and so on. So extreme tokenized, GneissWeb classification, readability. These are the ones that we are actually using. These so remember that these are the actual transforms, the Python code for each one of them, or Ray scalable version of these are under these directories of transforms, which are categorized based on either language or code or universal that applies to both code and language. So for instance, tokenization, rep removal, this is the substring deduplication that we talked about. These are here. So the individual transforms or the individual filters, the modules that we said they have been implemented and they are part of the repo. But what brings everything together are these recipes. So we go to the example folder on this, and the notebooks that we have, and the GneissWeb notebook, and if you click on this is the link that you were looking at before. So this is that particular notebook that allows you to go through, run. Half of this notebook is available to you as part of the repo, and we will just take a look at it. So it kind of solidifies in your mind what we were talking about in all of that theoretical stuff. So again, you'll say, look at the familiar diagram that I've shown you multiple times by now, and it is telling you there are links on the comment part of this GneissWeb dataset page on Hugging Face, the blog that we created, the technical paper. Any one of these will take you to the specific information. So like, let's say technical paper, you want to know more technical stuff, this is where the paper is. But any one of these links. So let's look at how you run this notebook. So first of all, for the repetition removal or that exact substring deduplication, you need to have Rust installed on your machine. So if you, this link here tells you how to go and install Rust, whether you have Mac or Windows or whatever. There are different versions, of course. You install that. And then of course this is you will make sure that this is part of your path. So it gives you, if it doesn't automatically adds the path for Rust compiler and so on to your path. This is you just to check to make sure that it is added, and because it is used by that particular. So then if you want to run this this notebook on your virtual environment, and of course this is the standard stuff, you clone our repo, and you get you get to this particular notebook that we are showing you. You create a virtual environment, you activate it, you install the Jupyter Lab in your virtual environment, and you fire it up. So then something that you will see here is the fact that, okay, so there's a little bit of explanation on the fact that some of these modules take a reasonable amount of time. They take may take up to an hour. So at any one of these steps, you will see that it says this step on a typical machine, on a typical Mac laptop, it took 0.6 minutes, and this step, the next step, took about 13 minutes, and so on. So this is sort of sets the expectation for you based on this particular data set, is how long it takes to go through this particular notebook. One thing that I want to emphasize here is the fact that because we are downloading these models, the models that we created on Hugging Face, you would need a Hugging Face token. So if you don't know how to do this, I think in our data prep kit pages on all of the transforms that require Hugging Face token, we have linked to how to obtain a Hugging Face token and so on. So you provide your own Hugging Face token, so that as you are downloading stuff from Hugging Face, you don't run into problem. These are read-only tokens, for instance. Okay, so then you pip install the data prep kit modules that you need to run this notebook. So here in this version of the notebook, this is before we kind of integrated all of those modules, the transforms, the rep removal, readability, extreme tokenize, and so on. So we had to specifically call out which one of them we are pip installing. But now in the next version of this notebook that will be available, I think tomorrow, you don't need to individually call out which modules of the transform. You just say language, and it pip installs. It takes a little longer, but it pip installs everything without you knowing the individual ones that you need, and so on. So in any case, this line here, this pip install part, which is specifically related to what you download or what you pip install from DPK, it will be one simple line: pip install data prep toolkit dash transforms all, or language. And so it will be much simpler than what you see here, and you don't need to know all the details. But in any case, let's go to the next cell here. So here we are obviously in this notebook. We don't want to go through the 15 trillion tokens and all the documents that are on FineWeb and so on. So we will download a typical Parquet file from FineWeb, and this is open. This is you download this particular. This is randomly selected here, so that you just go through this one, and you exercise the whole recipe from beginning to the end on this particular set of documents that are under this. So and then you resize it, you make it even smaller in order to make this more manageable. This is a filter that the resize is. You get this filter as part of the data prep kit. It comes automatically with that. It's not something that we developed for this particular GneissWeb recipe and so on. We already had that. And then we go through this exact substring deduplication, which we talked about. And these are the parameters. Many of them are, you use default values for many of these parameters. It allows you, this is using multi-threading, multi-processing in Python. So it allows you to run faster by taking advantage of the multiple threads and multiple processors that you may have, multiple cores that you may have on your laptop and run these things faster. So in this particular case, it took 13 minutes to go through this. So you define an input. The input is the file that you just downloaded from Hugging Face, and the result of this repetition removal. So again, remember this, the output format is a new Parquet file with the repeated sequences removed. So in that folder, in the output folder, you will get the Parquet with after removal of this. So this is the first step. So now we go to this annotation stuff, to the quality annotators that are adding columns to our Parquet file that identify whether this is high quality or not based on the criteria that we talked about, or based on the category, whether it belongs to science or medical and so on. So again, you go through, remember that we talked about two quality annotators. One is the custom made one that our GneissWeb team created, and then the DCLM one that exists in the open source. So you go through these two annotators and you annotate the document. So the output format for each one of these will be a new Parquet file with the label and score. The label that says this is based on, this is the label for quality annotator for the first one, and this is the label for the second one, and some sort of a score. So these are additional columns that are added to your document after running this step. So these are the two steps for running those two. Then you go to these category classifiers, the medical, education, technical, science, and so on. And you run them one after another. And each one of them adds, again, a column based on the name, medical label, medical score, education label, education score. And so you get, after this, you are getting 8 additional columns running these 4 in sequence. At the end of these steps, you have 8 additional columns with the column name and the score associated with each of these. So obviously, we are adding these columns, or other than the first step that we were removing documents. These are now additional columns, and so you can imagine that at the end we have to filter out based on some metrics on these qualities and some quality scores and so on. You have to sort of remove the low quality. We will get to that step in a second or so. So after doing this stuff, we go to that readability quality annotator. Again, that's based on some open source documents and knowledge and what the references here. Again, you will see them. I showed you in the chart where the references for this are and so on. So these are the McAlpine sort of readability score. So at the end of this step, again, one additional column is added, which is based on this readability of each one of these documents. So okay, and then finally the extreme tokenized document. So this is, again, we talked about this, and I showed you exactly what it means that a document is extreme tokenized. So then we have to identify the documents that are extreme tokenized, and so this step of the using this tokenization, it gives us it gives us the fact that this is, again, there are some sort of a again, it shows you the quality. If it's too much, if it's extreme tokenized, it means that we don't want it. We want to filter it out. So after going through all of these steps and running the extreme tokenized and all of these, now we need to apply a filter. And this filter, of course, this filter transform that you see, DPKT filter transform, this exists. This is one of the most powerful transforms that we have in Data Prep Kit. And so it's very important to construct, and this is the formula for using this filter and what gets removed and so on. This is exactly how it was done when we use this on top of that huge amount of data. So this formula, which says that if the DCLM fast score is greater than 0.002, I'm looking at this cell, the DPK filter cell, based on, and you will see this is a whole set of I'm sorry, a whole set of criteria for keeping or removing those columns that were annotated and so on. So this is the most important step. After doing all of that, what do you retain and what do you delete? And based on these formulas that are logical and ors, if this and this, and if this or this, and so on, you remove or you keep. You keep the columns from those documents. So that's the last step. And after applying this filter, you get your GneissWeb for that particular small amount of data. We just went through exactly how you would apply this to much larger amount of data. So hopefully this is, it would, if somebody starts with the real data, all of it, and of course you can't run all of it on one single laptop, but DPK allows you to run all of these transforms in parallel on a cluster with either ray scaling or spark scaling and so on. You will see that that's part of the details of the data prep kit that allows you this sort of the scalability of running these. So if you run all of this whole thing exactly with this recipe, with these filters and so on, that will reproduce the GneissWeb data set for you. So I think I just talk too much with too much detail. Let me stop here and let me stop sharing. I guess the best way to take it, but let me stop presenting and be here for any questions that may have come up during the presentation. I'm sorry that I didn't give you a chance. I did, and Dave, if there were hands raised and so on, I didn't see it. So, and if there are questions now, please. I don't know what the procedure is, Dave. Is it that you open the microphone or you still?
Yeah, yeah. Go ahead. We can start with the first question. We do have a question in the comments from Steve Wolf.
Yeah.
He asks, you mentioned that each node had 8 H100 GPU cards, but how many overall nodes were there?
Yeah, so I think there were 8 nodes in the experiments that we did. This was done with 8 nodes. So each one of them with multiple GPU cards and so on. Again, I don't remember the detail. I wanted to show you the reason I showed you that chart. It says that we did with LSF and we did this and so on. I wanted to show you that this is not done on a huge cluster because of the random sampling that we take and the way we are doing the evaluation. You do not need to run this on 15 trillion tokens to show the effectiveness of this. Yeah, 8 by 8, I think. Yeah.
Yeah, Jay says 8 by 8. So we're talking about 64 H100s.
I think so. I think that's what I saw from the presentation of those guys who did it. Yeah, that was my interpretation.
Got it. Okay. Well, great. Well, let's see. Anybody else have any questions? We did a good job of retaining our audience, so nice job. I do want to remind you, if you want to go check out Data Prep Kit, we've got a link there in the Slack messages, or Slack messages in the chat window.
Yeah. And I'm really hoping that you guys are real software engineers that want to go and try this out. So I really encourage you to go and using that small amount of data. I think the whole to run the whole notebook based on that data, that data file that you saw there, it takes a little more than an hour to run the whole notebook. So on a reasonable laptop. So
okay, and why don't Shahrukh, are you comfortable sharing the slide deck that you
Yeah,
presented?
absolutely.
Okay, if you
Yeah.
want to right now, if you could, I don't have access to it, but if you could, um,
What do you want me? It's
well, we should have everyone's email address. So I'll tell you what, let's do this.
Is there a way to share on this session and so people?
Yeah, you can do. Well, if you had a link, you could put it in the chat right here, and people could just download it. Otherwise, we can send it out with the email we send with the recording following this session.
Please do that, because I don't think I put my chart on any downloadable place right now. So
Okay, yeah. So we'll send a link to it in the email that we send to everyone. So as long as you registered via Meetup, we should have your email address. If not, you can contact me. I'll just put my email address here.
Okay, somebody has raised a hand, Dave. I see that. Alejandro.
Okay, Alejandro. Oh, Suji, somehow you have the slides. Okay, there you go. He has put them up somewhere and made them available.
Okay.
So check out the link that Suji's shared.
Oh, okay.
Okay, cool. Suji, are those the same slides? I think they are. Okay. Yeah. And there was a hand up. Sorry, Alejandro. Where are you? I can't see you for some reason. Where does it show hands up? Usually it pops you to the front here. Are you still there, Alejandro? That's interesting. Okay, so hold on. Here, we'll just turn on the microphone. Alejandro, if you're there, I don't see you for some reason, but if you have a question, if you want to ask it verbally, go ahead. Oh, maybe he's interested in the slides. Okay. So any other follow-up questions? Otherwise, we can start wrapping it up.
Yeah, I think one thing that I didn't show, the last slide, I don't think I showed, and I think maybe I just put that up for a second, if you don't mind. So,
Yeah, go
and
ahead.
that slide, the importance of that slide is the fact that it has all the relevant links in it. So if I share that, you will see that every single one of this. So that was sort of my summary chart. 2% average improvement on benchmark performance, a little more than 2%. And every one of these, if you click on the Hugging Face page, it doesn't it's taking you to the Hugging Face page, general Hugging Face page. It takes you to the Hugging Face page that it has the models, the custom-made models that IBM used for the classifiers and so on that you see. It will take you to that page. If you click on the data prep kit detail recipe, it will take you to the notebook that we were looking at. If you click on recipe models, again, it takes you to the specific models, and the announcement, of course, it takes you to the announcement that I also showed on the first page, and the paper would take you to the paper and archive that you just saw. So every one of these links is for more details and useful stuff. So okay.
Yeah, and Suji's link to that PDF file, I just double checked it. It has those links in that PDF file, so you can find all of those links at the end of that PDF file. All right, great. Well, we're just about time, so why don't we go ahead and wrap it up. Thank you very much, Shahrukh, for your presentation. It's very interesting. It's to see something so big and how how all the work that goes into making that kind of data available to the world. So thank you very much.
Thank you. My pleasure.
And everyone, so thank you again for joining us. Like I said before, we have talks every week on various topics. You can also join the AI Alliance if you go to the AI Alliance website at thealliance.ai. Click on community, and there's a few different ways you can join. You can you can also look for a working group, or just contact us. So with that said, I look forward to seeing you next week.